Hi and welcome to video Unit 1, Topic 1, Video 9 from the Specialist Maths content. And we're going to be talking today about combinations with restrictions. So we've done combinations in video 8, and it's worth making sure you've seen that or you're well aware of some basic combination rules. But here we're going to talk about restrictions where, for example, those 3 dot points there, an item must or must not be included, or 2 items cannot be in the group at the same time, or the group is split into parts, i.e. male and female. So let's have a look at an example. In example 4, a mixed touch team of 7 players must be chosen from 8 boys and 9 girls, such that there are no more than 4 of either gender. So we've got an A and a B, and it says, in how many ways can this be done? And then what if Brad and Jenny refuse to play together? So we'll have a look at the Brad and Jenny example, but not quite yet. First, we do need to do A. And this would be a classic complex familiar question if A wasn't there and it was just B, and then you'd still have to determine A first. So we're going to do A by considering 2 different cases, because we're picking 7 players, but there can be no more than 4 of one gender. So it's only 2 cases. We had the case where it's 4 boys and 3 girls, or the case where it's 4 girls and 3 boys. So let's have a look at these cases now for A. Case 1, which will be 4 boys plus 3 girls. So in this scene, we've got these 7 boxes to fill. I'll put a little line there, cut in half. They're the boys, here's the girls. Now, if I put down male there and female there, let's consider how many options we have. This is always a good visual way of doing combinations or permutations. So if we consider our options, there are 8 boys to choose from, so there is 8 ways of picking the first boy, 7 the second, 6, and then 5. Females, there's 9 girls to choose from, so there's 9, 8, and then 7. Now, this is assuming a permutation. Of course, if we take this back to a combination now, we recognise that this first student chosen could actually exist anywhere here. So we do that divide through and create the combination situation. So we could finish this calculation like this, and then divide through by 4 factorial here because of the double counting, and 3 factorial here. But instead, we're just going to use the combination that we know about. And that is, we need to do 8 choose 4 boys and 9 choose 3 girls. And this comes out with either 8 factorial over 4 factorial times 9 factorial over 6 factorial, 3 factorial, and simplify that. Or we can put it in our calculators, and we get 5,880 different combinations. And then, of course, we need to deal with case 2. And case 2 is 3 boys and 4 girls. And so we've got the same diagram there, but let's simplify it here. This is an 8C3 times 9C4 situation. And this works out to be 7,056. We expect that to be slightly higher because there are more girls and we're picking a larger number from that more girls. So that combination bit will be a bit higher. And therefore, the total number of options is equal to 5880 plus 7056. And that's equal to 12,936. So there's our total number of options and the answer to part A. So now let's consider part B. What if Brad and Jenny refuse to play together? So this is a really tricky question if we go about thinking of all the cases where they're not playing together. Now, because there's only 2 of them, it's not too bad, but there's an easier way. And the easier way is to consider all the teams where Brad and Jenny do play together, and then just remove that from the total number of teams. And this is a really common, complex question. So the teams where they do play together look like this. Again, we've got 7 cells, and Brad is one of the boys, and Jenny is one of the girls. Now, we've got to deal with the 2 cases again. So we've got case 1, and that is, case 1, where Brad is one of the 4 boys, and Jenny is one of the 3 girls. So there is 7 boys left to choose from, and we're choosing 3, times by 8 girls left to choose from, and we're choosing 2. And this comes out as 980. And then case 2 is where Jenny is one of 4 girls and Brad is one of 3 boys. So now we've got 7 boys left to choose from and we're choosing 2, times by 8 girls left to choose from, but this time we're choosing 3. And this comes out as 1,176, which gives us a total of 2,156. That's the number of teams that have both Brad and Jenny. So the total number of teams that don't have both of them, so might have Brad only, might have Jenny only, or might have neither of them. So without both, that's just equal to the total we calculated earlier, 12,936 minus 2,156, and that final answer is 10780. 10,780 options that don't contain both Brad and Jenny, and therefore they don't have to play together. Or, of course, you could actually sit down with them and say, look, just grow up a bit. So there's our first example. Now we're going to look at example 5. And example 5 I've denoted as a complex unfamiliar. Now, obviously, at this stage of the game, everything's kind of unfamiliar. But this is a complex unfamiliar because even once you've done this topic, it's a little bit different. And you'll be able to see it's a little bit different than what we are used to. So, a committee of 10 people will be chosen from 11 women and men. If the total number of possible committees containing at most 2 men is 11,561, determine N, the number of men. Okay, so we know that there's 11 women and we know there's N men, and we're choosing 10 people. So 10 will be chosen. So we've got an option, we've got a few options here, but we've got at most 2 men. So this instantly means we can break it down into 3 cases. And the 3 cases are, case 1 is 10 women in the committee. And that means there's no men, which satisfies this. It also means we don't have to worry about N. The ways that we choose 10 women is 11 choose 10. And the answer to that, 11 choose 10, is equal to 11. So we've got our first case solved. Our second case, case 2, is 9 women and 1 man in the committee. So the number of ways we could have this is if we choose 11 choose 9 for the women, and then N men choose 1. So we don't know how many men there are, but if there's N of them and we choose 1, then we get something. And I don't actually know what that is. I know the 11, but I don't know this one. And then we've got case 3. Case 3 is 8 women and 2 men. And so that is 11 choose 8 times by NC2. And this, again, I don't quite know, but we can do some calculations on this in a minute. So there's our 3 options. We can't have 7 women and 3 men because then that does not fit the at most 2 men criteria. And we know in total there was 11,561 options. So our sum is case 1, 11C10, plus case 2, 11C9 times NC1, plus case 3, 11C8 times NC2. And this sums up to, in equals over here, this sums up to 11,561. That's our total number of possibilities as given in the question. So 11C10 is 11. 11C9 is a calculation that we can do, and that's 55. And then NC1 is n factorial over 1 factorial n minus 1 factorial. And I'm going to expand this. In fact, I'm going to expand it now over 2 lines. So we'll just blow this up. This is 11 plus 55 times n factorial over 1 factorial times n minus 1 factorial, plus 11C8, which on my calculator is 165 times n factorial over 2 factorial n minus 2 factorial. And this is still equal to 11,561. Now I'm going to move this equal sign here anyway. And now I can solve this equation. So let's see how we go. 55 times by n factorial over n minus 1 factorial plus 165 times by n factorial over 2 times n minus 2 factorial. Now I'm going to change these n factorials. I'll change this one to be n times n minus 1 factorial, and I'll change this one to be n times n minus 1 times n minus 2 factorial. So I'm just reducing it down to match the minimum I've got in my denominator, 11,561. And now I'll cancel that out, and I've removed the factorial issue. So now I've got 11 plus 55 times by n plus 165 times by a half times by n minus 1. And this is looking a lot like I'm about to hit a quadratic. So let's simplify this quadratic and solve. It shouldn't take us too long, and I'll talk you through the solution. Hopefully this process is a bit easier. The first thing I'm going to do is remove that 11, which gives me 55n plus 165 over 2, which I'm going to write down as 82.5, n squared minus 82.5n equals 11550. Now I don't like 0.5, so I'm going to double everything, and we'll see how that goes. I've got 110n plus 165n squared minus 165n is equal to 23,100. Now I'm looking for some common factors. I can see, let's first of all simplify this. I get 165n squared minus 55n minus 23,100 is equal to 0. Now, of course, this is specialist maths, so you could go on, if you've got your graphics calculator in this question, which you should have because you wouldn't be expected to calculate these without it, then you could just go on and throw this in and solve it. But we'll go through the process. Everything divides here by 55 quite nicely, leaving me with 3n squared minus n, and then that divided by 55, I believe, is 420 equals 0. And then I can simplify 420 and 3n squared, etc. So if I go through the process there, I get 3n plus 35 and then n minus 12 is my simplification, which gives me 3n plus 35 equals 0, or n equals negative 35 on 3, or n equals 12. Now, obviously, n can't be negative, and it also can't be a fraction because it's a whole number of men that are selected for this committee. So n equals 12 is a much more reasonable answer. I go up here and have a look. At least 2 men, n has to be positive, n has to be a whole number, so 12 is the answer. So that's a pretty complex question, you can see there, but also, and take time to think about this, it's a question that can be done just through a process of setting up the cases, setting up the equation, and then solving with the knowledge you have from that basic combination form. All the best.